Okay. Well, I hope you guys are doing good. We are going to have our lecture 18 today. We're going to be talking about linear time invariant systems and how do you use Laplace transform to find the response of LTI systems. So let's talk about the description of an LTI system. We'll do it in three ways. There's an input to this system, the system itself is LTI, and the output is denoted as y of t. So if you wanted to describe the system itself or characterize the system itself, you have three different ways. One is talk about the impulse response of the system. What is impulse response? Well, if the input is delta of t, then the output is h of t. Right? That's the impulse response to this LTI system. That's one way of characterizing it, one way of describing it using the impulse response. So using the impulse response, how can I find the output? We are all experts at that, right? Just do a discrete convolution. Continuous time convolution. Now, if this particular system was a discrete system, then you would say x of n, y of n, delta of n, h of n. Over here, you would say y of n equals x of n convolved with h of n. But that convolution would be discrete. Right? That's one way of doing it. But you could also do this, right? You could also do something like this. You could say input is u of t. If the input is u of t, what is the output? Step response, right? What is the step response? Let me call that y step of t. Is there a relationship between step response and impulse response? Guys, remember step impulse derivative, right? Derivative of is it right? Derivative of impulse response is step response? No, it is the opposite. So instead of working with h of t, you could also work in unit step. Give it the unit step input, you get the step response, differentiate it, you got h of t. Using h of t, you can do the convolution with any arbitrary new input to find it output. So that's your second way of doing it. Now let's talk about h of s, working in the frequency domain. H of s is described as the transfer function of the LTI system. If h of s is the transfer function, what is h of omega or h of j omega? What is that? That is the transfer function, h of s. What is h of omega? Frequency response. So if I use h of omega, I'm going to understand the frequency response of the output given the frequency response of the input, right? But I want to describe the whole function, LTI. So I'm talking about the transfer function of the system, which is h of s. So using h of s, can I find out the output? Yeah, I can do that. If I know these things, x of s, if I multiply that with h of s, I will get output in Laplace domain. Then I can take the inverse Laplace transform of y of s to get my output, right? So multiplication in the Laplace domain, which is going to be the same as convolution in the time domain, and then do the inverse Laplace, which involves partial fractions and then using standard Laplace transform pairs, right? So that's your second method. Now the third method is, what if you are given the relationship between input and output? So we are trying to describe the LTI system, not using its impulse response or step response, not using its transfer function, but using the relationship between input and output. What could that look like? Well, for continuous time systems, it looks like an ordinary differential equation. So something like this. For example, you can have the first derivative of the output with respect to time equals x of t plus x of t minus 1. Right? That's a differential equation. It is giving you the relationship, direct relationship between input and output. Input is x, output is y. What is the relationship? You take the input x and you add the delayed version of x, and it will give you the first derivative of the output y. That's an input-output relationship. ODE, ordinary differential equation. What would this look like if this was discrete system? It would look something like this, right? It would look something like y of n minus y of n plus 2 equals, say, just making things up, 2x of n plus 3, right? Should I call this differential equation? What should I call it? Difference equation. So I've got a difference equation telling me the relationship between input and output for discrete systems, and I've got a differential equation or ordinary differential equation telling me the relationship between input and output for continuous time systems. But using this, I can still find y of t, right? How can I do that? So suppose I wanted to work with the ordinary differential equation over here. How can I find y of t over here? I can still go to the Laplace domain, right? The assumption is I know the input, right? So if I know the input, then I know x of s. Take the Laplace transform of x of t. Also find the Laplace transform of x of t minus 1 using the time shift property. So you're taking the Laplace transform of this guy, you're taking the Laplace transform of this guy, and because you know x of t, you know all of the other ones as well. You also take the Laplace transform of this guy. You're differentiating in time, you're multiplying by s in the Laplace domain. So you get s x of s, x y of s on the left side. So you've got s y of s on the left side, you've got a x of s, and then you have got x of s multiplied by e to the minus s because of the time shift. Using that, you can find out y of s divided by x of s, right? You've got h of s. You're back here, right? So again, you can take the inverse Laplace transform to find the output. So you can go from one to the other, but these are the three ways you could describe the LTI system. The goal is, for a given input, can you find the output or not? Three different methods. Questions about this? Impulse or step response? Next. Transfer function? Next. Input-output relationship. All right. Now, let's try to characterize the LTI system in the third way we did. What was that? Differential equation, or for discrete systems, difference equations. So what we'll do is, we have this x of t as any input, we have an LTI system, and we have the output indicated as y of t. And we are using differential equations, our third method earlier, to describe the LTI system. So if you use differential equations, then that differential equation in general form needs to be written in a very generic form, right? So let's try to write that in general. Let's say you have an input-output relationship of a general LTI system, general, right? Any LTI system will fit this. And we are going to describe that using the differential equation that looks like this. So let's try to take a look at what that is. On the left over here, you have multiple derivatives of the output y, right? So in our differential equation earlier, we just differentiated y once, but you could have second, third, fourth, multiple derivatives of y, and each derivative of y could have a scalar associated with it, right? In our case, we just differentiated y with 1, right? And our scalar associated with it was 1. But we could have 2 d squared y of dt divided by dt squared, right? So on the left here, we could have cap n plus 1 terms, where k is going from 0 to cap n. Ak are the scalars that are associated with the kth derivative of y of t, right? So kth derivative of y of t, we are multiplying with ak, right? So so if you had 2 terms, then you would look like 5 second derivative of y plus 10 first derivative of y. That's what left side looks like. On the right hand side, it's very similar, but now you have in x, right? So you have different number of terms. It is going from 0 to m, so there are m plus 1 terms here. The scalars are different on the right side, associated with the input, but the input is also getting differentiated, k times. How do I deal with constants? Or, well, when you differentiate x, you could get a constant. If you don't, then you have x of t, which could also be a constant, right? But on the left, you have multiple derivatives of y. On the right, you have multiple derivatives of x. And I want you guys to relate this to this, right? You had one derivative of y, and then you had just x of t plus x of t minus 1. So it was, we are not differentiating x, but you're just writing x with two versions, x of t and x of t minus 1. Let's go back here. Okay, so that's our general differential equation for any LTI system. N plus 1 terms there, m plus 1 terms there. With this, we will try to use the derivative property of Laplace. Every time you differentiate in time domain, you multiply with a s in the Laplace domain. We have seen this property, we have proved this property earlier. Even for Fourier transform, you had that same property. So let's try to apply that, because we are going to need to differentiate output as well as input k number of times, right? Where k is going from 0 to n for the output, 0 to m for the input. So using the above property for the system ordinary differential equation, what do you have? This is from before. Scaled versions of derivatives for the output, scaled versions of derivatives for the input. We will apply this property. What do you get? You are differentiating the output k times. In the Laplace domain, it is going to be the same as multiplying y of s by k times, so s to the k. And similarly, for this guy, you're differentiating the input k times. That's going to result in s to the k x of s. Of course, ak and bk are just scalars, so those are not going to change. They are going to remain as is. The summation is also going to remain as is. Now, to find h of s, which is the transfer function, what do? You do y of s divided by x of s. So you've got a y of s from here, you've got a x of s from here, just divide them to get h of s, right? So y of s, so when you need to find h of s, you can divide y of s by x of s, or the same thing you can do in this way. If you consider the input to be an impulse, if you consider the input to be an impulse, the Laplace transform of the input is going to be a 1, right? They both give you the same thing, right? They both give you a ratio of polynomial in S to another polynomial in S. They both give you the same thing. This is another way of dealing with that. So if you consider the input to be an impulse, x of s is going to be a 1, which is the Laplace transform of impulse, region of convergence everywhere. Y of t is going to be what? If the input is impulse, the output is going to be impulse response. What would y of s be? Well, we are using h of s to indicate that. The Laplace transform of h of t is h of s. So let's substitute that. X of s over here and y of s over here. What do you get? You get this. H of s times a polynomial in S where the highest power is going to n, right? So it's an order n polynomial. On the right side, you have another polynomial in S, order is m. H of s is simply going to be this guy divided by this guy. So you've got this as the numerator, this as your denominator. Now again, this could be an improper fraction or it could be a proper fraction. If it's an improper fraction, then you do polynomial division and get it into a proper fraction form, where the order of the numerator polynomial has to be less than or equal to the order of the denominator polynomial. So h of s is now what? It's in rational form, right? So you've got a polynomial in S for the numerator, another polynomial in S in the denominator. Let me just highlight their orders. For the numerator, you have order, what is that? M. And this guy is order highest power of S, right? N. Right? And what do you do from here? Well, you do partial fractions, and then you start with factoring, right? So you factor the denominator, you do the partial fractions, then find their individual inverse Laplace. So in order to find the impulse response, which is h of t, what do? You evaluate the inverse Laplace transform of h of s, which involves performing partial fractions, factoring the denominator, going through the partial fraction expansion, then finding out the inverse Laplace transform of each partial fraction that you got. Good. M is less than n. Why are you so scared of polynomial division? All right, that takes time. All right. Yeah, that would be cruel. Sorry. No, I'm not doing that. Yeah, I don't think anywhere on Signals and Systems catalog it says test the ability of doing polynomial division. So I'll not do that. So fair question. The answer is no. I will give you proper fractions. Let's move on. How about the step response? So we have talked about dealing with a linear time invariant system, describing it using the impulse response, but very similarly, you can do that using even the step response. So let's talk about that. You guys remember the connection between impulse response and step response, right? The derivative of the step response is going to give you the impulse response. We just sort of reviewed that earlier. Now, if you take the Laplace transform of this guy, what do you get? H of s over here. Derivative gives you a multiply by s. You're just differentiating once. So you get s to the 1, and you get step response also in the Laplace domain. So take the Laplace transform of the output. Earlier, output was step response. Now you take the derivative of the step response, which was impulse response. You take the Laplace transform of both sides, what do you get? For this, you get h of s. For this, you get s, y step of s. Y step of s indicates the Laplace transform of the step response. Now, you can rearrange to just write step response in Laplace domain is 1 over s multiplied by h of s. And you can sort of see this, right? Like this is pretty easy to. What is 1 over s? Can I say that 1 over s is the Laplace transform of u of t? Yeah. So input, output, input, transfer function, you got output, right? So 1 over s for the input Laplace transform, h of s for the transfer function, you get y of s. So this sort of validates this statement that impulse response is the derivative of the step response. Another way of doing this would be in the ordinary differential equation. In the differential equation that involves a bunch of y's and x, right, in time domain, use x as unit step and y's all replaced by step response, right? So if you change all the inputs to u's and change all the outputs to the step response, now you have a differential equation that is involving u's and y step. What can you do when you go to Laplace? What do you have? For these guys, you will use 1 over s, right? And for these guys, you will use y step of s. So you can transform that differential equation in the Laplace domain, and you will be left with all of these guys. Y steps for this, 1 over s for this. You rearrange, you get y step of s, take the inverse Laplace transform, you're back to y of t, the output of the LTI system, which was the goal, right? Okay, let's move on here. Do an example. Now, just to save time, I've already done the example. One thing that I want to point out, which can be stressful, is this. 5s. You're doing this in a hurry on an exam. You're writing 5s, and there are s's along the way. What can happen? You can mix up. So many times it has happened that the students got messed up with their own 5s and s's. So, be aware of that. I think that's the first step. The way I deal with it is to write like a very cursive S, figure out the way that works for you. I can't. Listen, the problem with that is I have promised people, literally I have promised people that I will never have fives in the problem, right? But when they were solving it, I can't control how they solve it. So if people have fives, oh. So here, there's no way for me to control that, but I want you guys to, before you actually face the problem while doing a homework problem or an exam problem, just be aware that that can happen. All right, so what are we doing here? We have a differential equation. On the left side, we have some derivatives of y that are given, and they are related to some derivatives in x. So this is a input-output relationship for a continuous LTI system that we are describing using an ordinary differential equation. The goal is what? The goal is essentially to find the transfer function h of s, and once we find that, we take the inverse Laplace transform of that to get h of t, right? So what do? You straight away go for applying Laplace transform on the entire equation. Second derivative of y becomes s squared y of s. 5 times the first derivative of y gives you 5 s raised to 1 y of s, right? So you are essentially writing the Laplace transform of these terms. Here, 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 and here. Guys, see that? Oh, go ahead. So not so far. So far we are not. So we are assuming that initial conditions are all 0 right now. Later on, we'll talk about unilateral Laplace transform, where we will have initial conditions. That's a very good question. So right now we are assuming that anything that has happened at time before 0 was 0. There was no initial condition, which is not always the case. So we'll talk about even that case with initial conditions slightly later, which is not going to change this procedure. Is going to add more terms to our equations. Let's see. So once you get this, right, factor out a y of s from here, factor out a x of s from here, you get this. Then h of s is simply going to be y of s divided by x of s. That's your transfer function. You got s plus 1 over here. You have got in the denominator a quadratic in s. Factor it. You got s plus 1 in the numerator. You have got 2 factors of s in the denominator. What do you do from here? You do partial fraction expansion. It is already in a proper fraction form. So you get what? K1 divided by s plus 1. S plus 2. Plus K2 divided by s plus 3. Find K1, find K2. Using residues, you get -1 divided by s plus 2 plus 2 divided by s plus 3. So far, you guys have done this process, right? You guys have seen this process at least multiple times. I'm not spending much time there. How do I find K1? Let's just talk about that. How do you find K1? Well, this is the value that is residue when s is -2, right? So just put s -2 here. Remove this guy, put -2 here and -2 here. What do you get? In the numerator, you get -1. In the denominator, you get 1. So K1 will be -1. And similarly, you find K2. Next, I have found h of s. I have put it into a form on which I can apply standard Laplace transform results. So the inverse Laplace transform of this is what? For this, I get -1. 1 divided by s plus 2 gives me e to the -2t u of t. That's a standard pair. What am I using? I'm using 1 divided by s plus a, right? Similarly, for this guy, it would be 2 e to the -3t u of t. And since I have assumed that there's no initial condition, I'm assuming that my signals are right-sided. That's why I got u of t's instead of u of -t's. Questions about this example? How do you find, given an ordinary differential equation, given the input-output relationship, how do you find h of s, transfer function? How do you find impulse response? Now, once you find the impulse response or the transfer function, actually, you can go anywhere, right? You can find out outputs to any given new input. You can find step response. You can do everything that has to be done that you could ever possibly do with that LTI system. You can do that now. So the only thing that you have to be sort of careful is the 5 and the s. it can be frustrating during an exam. Imagine doing this 5 minutes left and you're trying to go over it and you lose your own handwriting. Has happened. Was that? Well, sure. That's one strategy, but I've heard a lot of frustration from students when they see a 5 in there. They they was that another letter for S? Actually, there was a student who actually used X for it, did the whole thing, and then reverted it back. Do it. Was that Q instead of S a Q? 9 maybe, yeah. 6. We need more letters. All right, moving on. What was that? Happy face, smileys instead of S. All right. Now let's talk about one very, very important thing. What is that? Stability. Where should the poles of my transfer function be so that the system is stable? And I think we can design like a t-shirt, very nice t-shirt, saying the poles of my system are in the left half of the plane. And that could be like a very in joke, right? Inside joke. People who are in controls understand that. If your poles of your transfer function of your system are in the left half of the S-plane, that indicates stable behavior. If you are in the right half, that is unstable behavior. So by just looking at the location of the poles, you can find that out. But is there math that supports that statement? Let's try to look at that. The initial part of the slide over here, you have seen before. What is that? Express the transfer function as a ratio of polynomials, as a rational transfer function, a rational Laplace transform. You have got a numerator polynomial, we are calling that P of S, and we have a denominator polynomial, we are calling that Q of S. That's a transfer function, right? H of S is a transfer function. Now, whatever the roots are for P of S, those are going to be values of S for which the transfer function goes to a 0. Hence, they are called zeros of my transfer function or zeros of my system. Q of S is the denominator polynomial. So the values of S that make Q of S go to 0, or in other words, make H of S go to infinity, are going to be considered the poles of my transfer function. So you've got the roots of numerator, you have got the roots of the denominator, you're calling them zeros and poles respectively. With that information, you can actually sketch out a pole zero plot. Now, at the beginning, this pole zero plot might look very, very innocent, like it's so simple. Yeah, I just have to draw x and y axis, make crosses and circles, right? Very simple. However, you will see that our next 2 lectures or 3 lectures will have everything to do with those pole zero plots, because we are going to change certain aspects of our system. What is going to happen to the poles? Those are going to move around in the S-plane. So as we change our system, we will track the movement of the poles. If they start with the left, in the left half plane, and stay within the left half plane, then that indicates that no matter what you change in the system, you will be stable. But if you start the system stable, location of the poles is in the left half of the plane, you tweak something in the system, the poles will move, and you can track that movement. That movement, or the poles moving in the S-plane, is called a root locus plot. We will sketch that. We will learn the rules for that. If it moves over and comes to the right half of the plane, that becomes unstable. So in reality, it's becoming unstable, and there's math connecting that. So we'll do a demonstration with an inverted pendulum and all that. We'll do something fun related to that. So right now, we are at the initial point of that. So it will seem very simple. Try to tell me what are the zeros. Well, what are the roots of the numerator? 1 and 1. So you have repeated roots at real sigma equals 1, right? This is only real. So when sigma equals 1, you have two zeros of this x of s right here. Sometimes you can point that out as two circles, or you can just put one circle and write 2 on top of it. That's the repeated roots. Those are the zeros. Next, look at the denominator. You have got two factors here, s plus 1 and s minus 2. That means that you have got two poles that are distinct. One is at -1 and the other is at 2, marked here and here. On what plane? S plane. What is the x-axis? Sigma, real part of s. What is the y-axis? Imaginary part of s, j omega. Well, I should say j times imaginary part of s, which is j omega. In this case, my zeros and poles are all lying on the real axis. Does it have to be the case? Not necessary. Your poles could be complex, your zeros could be complex as well, right? So you could have poles here, you could have zeros here, you could have, in general, you can have the zeros and poles anywhere. Let's move on. We were trying to design that t-shirt, right? Poles in the left half of my S-plane. Is there math that supports that statement? To track that math, we will start with finding out what the location of the poles is for a stable system. So let's suppose you did this. You did what? You represented h of s as a rational Laplace transform. You did all the partial fraction expansion. After that, what does it look like? H of s will look like this, right? Sum a1 divided by a pole at p1, sum a2 divided by a pole at p2, and so on up to sum an, some scalar an, giving you a pole at Pn, right? So n poles, that's in general. Yeah? You guys agree with this so far? Any h of s, which is a polynomial s in the numerator and denominator, you do partial fraction expansion using one of those rules that we discussed at the end of last class, you end up with this. Now, once you end up with this, what are you trying to go for? You're trying to go for the inverse Laplace transform. So you're taking the inverse Laplace transform of each of these n terms. Inverse Laplace transform of this. Yeah, I know this, right? Because it is in the standard form. I just need to scale by a1. So what is it? The inverse Laplace transform will simply be a linear combination of e to the p1t, because the inverse will be what? It will be a1 e to the p1t u of t, right? For each of them. It will be a linear combination that has the amplitude will be scaled by e to the p1t and e to the p2t, e to the pnt. What we want is for that exponential to go down as time goes up, right? You want s to decay. So you want p1 to be negative. Let's see that. If p1 is negative, e to the minus 5t, e to the minus 10t, then that exponential is going down. If the p1 is positive, e to the 2t, 3t, 4t, then that exponential is growing, not converging, not stable, right? So, and j omega is not helping us with the magnitude anyway, right? E to the pt, if a pole is p at p, you can write that as e to the sigma plus j omega t. E to the j omega t will just give you a magnitude of 1. That doesn't contribute. The only thing that contributes is sigma. So what that means is the real part of the pole, right? Wherever that pole is, the real part of that pole has to be negative. If it is negative, then that exponential will be going down, indicating stability. You see that? So you have sigma less than 0, making the absolute of e to the pt converge to 0, right? Decaying exponential as time grows. So that's good. That's stability. But this guy is unstable. When sigma is greater than 0, what is sigma? Sigma is the real part of the pole p. Earlier we had n poles, right? So you get sigma 1, sigma 2, sigma n. All those sigmas have to be negative in order for the entire h of s to be a stable transfer function, stable system. So due to this, when we design systems, we want the real parts of the poles to be negative. Like I said, poles do not need to be only on the real axis. They can be anywhere in the complex plane. but the real part has to be negative, which essentially means they have to be in the left half of the S-plane. If they move to the right half, unstable. In fact, if they even move to the vertical axis, then it is marginally stable. Poles with negative real parts, the system is going to be called asymptotically stable system, which essentially means as time moves on, it will become stable. So pendulum, I'm applying a force. Is it asymptotically stable system? If I move it, it's going to come and stable, right? That's a stable system. As time goes on, it becomes stable. This guy, I'm trying to balance it on my hand, right? This guy, suppose in order to make it stable, I'm moving my hand, right? I'm moving my hand here and here. I'm trying to balance it by moving my hand. If I leave it and absolutely everything lines up, right? Center of gravity, and I'm not moving at all, it's just going to be stable, right? But that's a theoretical thing, like no air and no force being applied, absolutely nothing in vacuum, it's going to be stable. That's called a marginally stable system. A little bit of movement is going to fall down, right? So that's a marginally stable. So for that particular case, I'm going to find that the poles are actually on the j omega axis. But when you have a pendulum, the poles of this particular system are going to be in the left half of the plane, telling me that as time goes on, you will become stable. You will converge. All right, so let's take a look at the connection between how does the impulse response look like for different type of systems. And I'm classifying them based on the stability. So let's talk about stable, unstable, and marginally stable. So let me just write those three things down here. I have something that is stable. And here I have unstable. And I have marginally stable here. And I just want to observe the impulse response of such systems. What that means is I have a system here. I gave it some energy, right? Some impulse response, some impulse. I want to monitor what happens at the output. For a stable system, and I'm assuming that it's a causal system. So that means that before time 0, I have nothing, right? Time less than 0, I have nothing for the output impulse response. If it's a system stable response, if I give it impulse, I will get something like this. A response that decays with time. As time goes up, it converges. That is a stable system or asymptotically stable system. Unstable would look like what? Give it energy, growing with time, right? Audience, public setup. There are microphones that are connected to audio amplifiers with a high gain, feeding back to the mic, right? Speakers feeding back to the mic. What is happening there? It's a positive feedback environment giving you a very uncomfortable sound. Impulse response looks like this, right? Even if you tap a little bit, it'll go like loud sound, right? Next, marginally stable. What is that? I'm going to be dancing, right? Balance here, 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 right? So that is, I will have oscillations, but they will essentially not grow, not die. They will just be there, right? So this is going to be bounded, but the stability is going to be marginal, right? It's marginally stable, because a little bit here and there, you're going to go up, you're going to explode, right? So you will get oscillations. So this is what you guys see this in RLC systems, right? RLC transient response, decaying exponential with sinusoids and growing exponentials with sinusoids, and this is just sinusoid, no exponential damping. So that is related to system stability. So if you treated those responses as impulse response, that's related to stability of the system. Questions about this? All right, so we talked about this in terms of impulse response, right? But does it always have to be impulse response? Can I talk about same things, but with respect to a step response? If I give a step, I can also monitor the step response and be able to comment about stability, right? So if I have a step from here to here, what would the step response look like for a stable system? It'll shoot up and then it'll die down to the step, right? So that's a stable response. What would be the unstable look like? It'll shoot up and then it'll keep growing up as u of t goes on. For marginally stable, it'll just keep oscillating, right? Just oscillations. Next, let's try to mathematically describe those three conditions: stable, unstable, and marginally stable. And we are going to do that asymptotically, right, as time goes to infinity. So we have causal systems here. H of t is 0 for time less than 0. Our LTI system looks like this. So input x of t, impulse response h of t, output y of t. In the Laplace domain, x of s, transfer function, y of s. So for these things, we are trying to classify stability. So an asymptotically stable system is a system when input is 0, right? You have removed any input, then the output has to die down to 0 as time goes on. If you don't give it any input, the output eventually has to go to 0 as time goes to infinity, as time goes on, right? Asymptotically decays. If you don't, asymptotically decays if you don't give it any input, any new input, which essentially refers to stability, because we have already said if a system has to be stable, then the poles have to be having negative real parts, which means all poles have to lie in the left half plane. Asymptotically stable systems, poles are in the left half. Let's just put it here. 1, 2. Poles are in the left half plane, right? And you could have repeated roots as well, right, over here, 2 of them. So no matter if they are repeated or they are distinct, they all have to be in the left half plane. Cannot include j omega axis, right? They cannot include j omega axis, and they obviously cannot be on the right half. Always have to be on the left half. So roots of the denominator polynomial has to have negative real parts for this system to be considered as asymptotically stable. Questions here? All right, next, marginally stable, just about stable. What does that look like? If you remove the input, then the output may not go to all the way to 0, but it will be bounded, right? There are oscillations, they are going to be there. So oscillations are going to be there in the system, but it will not grow, it will be bounded. So if you remove the input, the output will be bounded as time goes to infinity. So the fact that it is not growing to infinity makes it stable, but just marginally. Over here, an LTI system is considered to be asymptotically marginally stable if and only if it satisfies these two criteria. One is no roots in the right half plane. You cannot have roots in the right half plane. Why? It will make it unstable. And you cannot have repeated roots on the j omega axis. So you cannot have something like this. However, you can have something like this. So I have got two roots on the j omega axis, right? This is sigma, this is j omega, this is my S plane. On the j omega, I have got two poles, but they are not repeated roots. They are not at the same location. That makes it marginally stable. You cannot have them on the right half. Go ahead. Left half, they are already stable. Yeah, so I wouldn't need to classify them as marginally, right? So if they are in the left half only, left half and on the j omega axis, marginally stable. Yes, so if you have it here and here, this is keeping it stable, but this is making it marginally stable. So you would call that marginally stable. Other questions? You just cannot have repeated roots, right? You cannot have multiple on the j omega axis at the same location. You can have them distinct, but you can have them multiple, repeated. Next, whatever is left, asymptotically unstable. So if you remove the input, the output grows as time goes on. That's an asymptotically unstable system. For this, you need to have at least one root in the right half plane. Even if you have one pole in the right half plane, you know it's going to be unstable. Or if you have repeated roots on the j omega axis. So if you have repeated roots on the j omega axis, or you have at least one pole, then you know that it is going to be unstable. Go ahead. So e to the minus t, p of t, you have another one on the same one, right? So when you take the inverse Laplace transform of that, you have got 1 over s, then multiplied by 1 over s, you have got 1 over s squared. So what happens to that in the time domain? You get t u of t. What does t u of t look like? Something that grows, right? Other questions? All right. Fourth way to classify stability, which is now bounded input, bounded output. A system, an LTI system, is considered to be bounded input, bounded output system if and only if output is bounded as long as input is bounded. So if you keep giving it a bounded input, a sine, a cosine, e to the minus t u of t, all these are bounded inputs. A constant, all of these should result in a bounded output. If that is the case, then it is BIBO stable. What is the relationship between asymptotic stability and BIBO stability? If a system is asymptotically stable, then it is considered to be BIBO stable as well. If a system is marginally stable, then it is BIBO unstable. And of course, if the system is asymptotically unstable, then it is also bounded input, bounded output unstable. So the only real thing over here that is sort of new is, or we are learning, is this. If a system is marginally stable, then it is going to be bounded input, bounded output unstable. So something that was input was bounded, but still it would give you an output that could be unbounded. Next, unilateral Laplace transform. So that's what we are talking about. What if you don't have causal response? What if you have some initial conditions? How do you deal with that? Well, the one-sided Laplace transform, which starts at a time that is before 0, is defined as f of s is, instead of negative infinity to infinity, you have 0 minus to infinity. Same equation, f of t e to the minus st dt. That's your one-sided Laplace transform. So both these transforms, bilateral, the one that we have seen before, and the unilateral one that we are seeing right now, will share almost all the properties except for the time differentiation property. So the time differentiation property is going to have an extra factor. Let's take a look. When you look at bilateral Laplace transform, the more derivatives that you take in the time domain, you simply increase the power of s in the Laplace domain. S squared, s cubed, and so on to s to the n. However, for a unilateral Laplace transform, the first derivative of the function, if you differentiate the signal one time in the time domain, that will give you f of s, but you also have to remove the value of the function that was just there at 0 minus, right, just before it started. This is what? Evaluating the time domain function at time 0 minus. So taking f of t, substitute. So initial conditions have to be given, right? Only if initial conditions have to be given, then you can evaluate this. Next, if you take the second derivative of the function in time domain, you would get s squared f of s, just like bilateral, but you'll also get minus s f of 0 minus, and differentiate the signal f of t and find the initial condition for that. And if you keep doing this, you will get this. In general, if you differentiate the signal n times in the time domain, in the Laplace domain, you will get this term exactly the same as the bilateral Laplace transform. So that is Laplace transform because of the input that has come after 0. But because of the initial conditions, you will also have all these terms. This involves differentiating the signal in time domain and plugging in for the initial condition. So they have to be given, right? So initial conditions have to be given for all these cases here. Let's take a look at an example. But just before we do that, we'll talk about some motivation for initial condition. What is that? Now, two things can happen, right? So you see, there's one system. You're providing a new input and you're getting an output because of that input. But you also had initial conditions. Because of those initial conditions, you're going to get a different output. So you need to evaluate the output as a sum of two outputs. One is the response to the input, the other is the response to the initial conditions. Can you see that? That's what we are going to talk about here. Most LTI systems can be modeled using ordinary differential equations. Systems with no initial conditions, you apply the bilateral Laplace transform. Assume that you have no initial conditions and you will be able to do that directly. You don't have to worry about the initial conditions in that case. We did an example there for this. But if the systems have initial conditions, then you deal with the unilateral Laplace transform. So for this, the response of the LTI system will have two pieces. One is going to be y z sub I, and then the other is y sub zs. What is zi and zs? Zi is 0 input, zs is 0 state. What is that? This is response due to the initial conditions, right? So this is response only because of the new input that I gave, no initial conditions. And this is because of response due to the input. So this is 0 initial state. You guys see that? One is response due to the input, the other is response due to the initial conditions that were there. Okay, so far, yeah, because of the input, and this is the initial condition. So you can say that for the bilateral Laplace transform, we were only considering the input, right? Like we were not looking at the initial conditions. For bilateral one, we were only looking at this guy. 0 state. You are assuming that the initial state is 0 state. Let's do an example. Over here, color coded over here, so you guys should be able to follow it along really well. And 5 present over here as well. All right, so let's see. Find here. You're given a differential equation, and there are some initial conditions that are given as well. Without initial conditions, you would have to treat that as a bilateral Laplace transform. But you are given the initial conditions over here, you're going to treat that as a unilateral Laplace transform. So you've got the differential equation over here, relationship between the input and the output. You are given that the output just before 0 was a 2, and the output, the first derivative of the output just before 0 was a 1, and you are using the input for those particular output. You are considering the input as e to the minus 4t u of t. What you want to find out is y of t, right? So given this particular input-output relationship, find the response when the input is this. And it is conveniently in a very good form, e to the minus 4t u of t. You know that the Laplace transform is going to be very simple, right? 1 divided by s plus 4. So let's try to do that. For this guy, I'm using unilateral Laplace transform. So I've got s squared y of s, but I've also got minus s y of 0 minus first derivative of y just before 0, because that I'm using this from here, right? Next, all these formulae are all there on your Laplace transform and z tables, so you don't need to memorize them by anyway. So you have got the Laplace transform of this guy over there. For 5 y of t, you have got the Laplace transform there. Again, we are using unilateral one. 6y of t, that should be easy, just 6y of s. On the right-hand side, you have got first derivative of x. So that means using unilateral Laplace transform, you have got 5. Oh, what? Oh, s, right. The only thing that is 5 is over here. S x of s minus x of 0 minus. And then x of t will give you x of s. Now, because I'm given x of t, I can evaluate this guy and this guy, right? X of s is going to be 1 divided by s plus 4. And this guy is going to be what? Just before 0 is going to be, what is that? Input at time 0 is going to be a 1, right? Substitute the initial conditions. What do you have? You have y of s. Let's see. X of this guy is given to me as 2. Next, this guy is a 1. Substitute that. This guy again is a 1. Right, and then this is a 1. So if you put in all those things, so go ahead. Oh, you're right. You're right. Because of the u of t, I don't need to have this goes to a 0. It's only defined for time greater than 0. Yeah. Next, substitute these values. Manipulate the equation such that you have y of s terms separated, x of s terms separated. Divide it out. You have got what? Y of s, you are going for y of t, right? So you have to find the inverse of Laplace transform of y of s. X of s is going to be Laplace transform of x of t. X of t is either minus 40 u of t. Laplace transform is 1 divided by s plus 4. So you can substitute this guy over here. Rewrite y of s. When you rewrite y of s, you will see that you get s plus 1 divided by all of this. And you will also get 2s plus 11 divided by all of this. And you can actually separate this out into 2 blocks. One is for 0 state, one is for 0 input. So it's, how are you able to do that? You are able to do that because you can keep track of which ones are coming due to the unilateral Laplace transform, right? So for example, this guy, this guy, this guy, and this guy, right? These are the only 4 things that are appearing because of the initial conditions. If you combine all of that and then remove the other ones, you can separate them out into 0 state and 0 input. If you wanted to find them out individually, if you wanted to find out what is the response due to this and what is the response due to this, then you need to separate them out. But if you don't need to find them individually, then you can treat them all at once. Go ahead. Yeah, absolutely, absolutely. Yeah, exactly. Now you have got y of s as 2 fractions. Each of these fractions you can do the partial fraction expansion and then do the inverse Laplace transform. So for this guy, you have got those partial fractions. Again, proper one. Numerator order is 1, denominator order is 3. So you guys should just be able to use k1 divided by s plus 4 and k2 divided by s plus 3 and k3 divided by s plus 4, right? So you get these 3 terms there. For this, you get 2 terms. Again, k1 and k2 will do it. All right, so from here, use the standard forms. Negative half e to the minus 2t plus 2 e to the minus 3t minus 3 over 2 e to the minus 4t and so on. So you get all of this. For the red ones, the 0 state, right? This, and this. And then for the 0 input, which was here, you got that, and then the response of that is this. So you have the total response. Some of those things are for 0 input, some of those things are for the 0 state. Questions here? Solving an ordinary differential equation with initial conditions. Go ahead. The inverse Laplace transform of these terms, right? say s divided by s plus 2. Yeah. So e to the minus 2t u of t for that, and then multiplied by 7, of course. Questions? All right, guys, okay? Let's see. For an LTI system to be causal and stable, all the poles must lie in the right half plane, left half plane, right? We have talked about that. Stable means left half. And the region of convergence is going to be to the right of the rightmost pole. Why is that? Because the signal is causal, right? If the signal is causal, is moving right. As time greater than 0, it's moving right? It's causal. For a right-sided signal, we know the region of convergence should also move right. So what we have is, let's try to sketch up some arbitrary pole zeros. Just poles. So I have this guy, and then I have this guy and this guy, right? I've just made up like 4 poles for my system. I want to find out, and it is stable, right? All the poles are in the left half plane. I want to find out where the region of convergence is going to be if I consider that system to be causal. If I consider that to be causal, then I have right-sided signal for which the region of convergence is going to be to the right of the rightmost poles. So I'm just going to draw a straight line here, right here. And then I'm going to sketch the region of convergence. It is going to include the j omega axis, right? For causal and stable, you will have a ROC that will include the j omega axis. Now, you see what I can do is, as I tweak parameters in my system, these poles will start moving, right? This might move left, this might move right, they will move. And there are lots of rules that dictate that movement, and we'll study those. But as long as these guys move here, you are fine. If they move here and cross over, then you are unstable. Questions about this example? Okay. Next topic. Oh, go ahead. Next topic in our discussion, filter design. Which ones? Butterworth filters. We are going to design them. We are going to design low-pass filter. And what you'll learn is filter transformation. So we'll deal with 2 types of filter design. One, designing a low-pass filter. And how can you do a filter transformation to get to a band-pass filter? Let's try to see how much we can do today. We'll be focusing on Butterworth filters. So essentially, where should my poles be, right? So essentially, what this topic will allow us to do is, I can design my own system. You just tell me what type of filter do you want and what is the bandwidth, what is the cutoff. I will be able to tell you where you should put the poles, right? Where should you put the poles so that you get a low-pass filter? Not ideal one, a Butterworth one, so a realistic one. Should be stable, of course. So right away, you know that the poles are going to be in the left half. Before we do that, let's try to understand some terminology. And to understand terminology, we'll look at some ideal filters. What do you have in sketch number 1? You have an ideal low-pass filter, also called as a brick wall filter. The frequency response of these filters is given, h of omega versus omega. Omega c is the cutoff frequency. What is the magnitude of the frequency response below the cutoff frequency? It is 1, right? So h of 0 is 1. As that frequency goes to infinity, it is going to go to 0, right? So can I say this? For a low-pass filter, at low frequencies, you want that to be maximally flat. Flat in the frequency, right? The frequencies that it is passing, you want it to be flat in that frequency zone. Why? Because you want those frequencies to be treated equally. Yeah? What do you want it to happen as frequency goes to infinity? You want it to drop, right? So maximally flat within the pass band smoothly goes to 0 as omega tends to infinity, right? Those are the two properties that define Butterworth filters. That's it. What is maximally flat? Flat. What is a mathematical way of saying maximally flat? What is constant? So how do you do it mathematically? Derivative goes to 0, right? So derivative of the frequency response should go to 0 when omega is close to 0. Yeah, that's mathematically flat. What is smoothly goes to infinity? As omega goes to infinity, it has to go to 0. In other words, as omega goes to 0, it has to go to 0, right? 1 over omega. You can reverse that. Instead of saying omega goes to infinity, you can say 1 over omega goes to 0. So those are going to be our steps that we will use deriving the Butterworth filter. Again, we'll take a look at that later on as well. So next one, ideal high-pass filter. Frequency response shown. Any frequency that is higher than omega c is getting passed, and all those frequencies are getting treated fairly, same way. So amplitude 1, amplitude 1. That's a high-pass filter. At 0, nothing. As you go up in frequency, you've got a 1. That's an ideal high-pass filter. That's an ideal band-pass filter. It is passing the frequencies between omega 1 and omega 2. Almost like taking a low-pass filter and moving it up in frequency. So what do you have for a band-pass filter? Well, the bandwidth is omega 2 minus omega 1. At 0, it is 0. At infinity, also it is 0. Only for a certain band of frequencies, it is 1. So in order to design a bandpass filter, what we'll do is we will first design a Butterworth low-pass filter, and then we will transform it into a bandpass filter. Again, all of that discussion is going to happen next. H of omega is going to be 1 only between these two frequencies, omega 1 and omega 2, which is essentially my bandwidth. Omega 2 minus omega 1 is the bandwidth of my bandpass filter. Last one, band stop filter, your fourth option. The band of frequencies between omega 1 and omega 2 are getting stopped. Every other frequency is getting passed. At 0, you've got a 1. At infinity, you've got a 1. Only between omega 1 and omega 2, you've got a 0. Band stop filter. So we'll deal with 1 and 3 here, low pass and band pass. There's all pass filter as well. Don't do any discrimination to frequencies, just pass all the frequencies. What is an example of an all pass filter? A delay element is an example of an all pass filter. The frequency response is essentially e to the minus j omega t. So what is that? That is a delay system, right? So if you have a delay, if x of t goes in and say x of t minus cap t comes out, that's a delay system. So when you're delaying, you are not discriminating with frequency, it's passing all frequencies. All you're changing is the phase. Why are ideal filters not practical? Why is this not practical? Let's do simple case. Why is the low pass filter not practical? What is it? That's not how. Yeah, it is ideal, but why is it not practical? So the shape is rectangular, right? Why is that? Why can't you get that sharp turn? If you had infinite number of capacitors and inductors, then would you be able to get it? Good. Right. So, okay, here. What would be the impulse response of this ideal low pass filter? A sink. A sink goes on for how much time? Forever, right? So impulse response of this is going on forever. So if I actually want to filter it out as a ideal manner, then I want this to be observed forever. Impulse response is going to infinity. That's not practical. You have to limit it for some time. You can say, I'm going to send something, but I'll use that for, say, 6 nulls, right? 6 time periods of that sink, or 3 time periods of that sink. You cannot say forever, right? That's the reason why your Ideal filters are just ideal, they're not practical. So sync is, what is that? Not time limited. So what you literally do in communication system is to chop off the sync. You don't take it from negative infinity to infinity. You just take it from, let's say, 3 periods on the right, 3 periods on the left, done. That's your sync. The more, right? Like, so what is that going to do? Well, you're going to have to wait forever. So the amount of time that you wait to observe the output of the low pass filter is going to shoot up, right? The latency is going to increase. So input goes in, the ideal low pass filter output is not coming. It's not coming. It's not coming, right? You're just waiting there. So again, it's a trade-off, the classic trade-off for engineers: performance versus cost. Let's see. So Butterworth filters are going to allow us to get that practical version of those ideal filters. Practical filters that can be derived using various approximations to an ideal brick wall filter. For these, for the derivation of the Butterworth filter, the Taylor series expansion is going to be something that we'll use a lot, right? So we are going to leverage Taylor series approximation. What is Taylor series? Any function f of x can be represented as the value of the function at 0 plus the first derivative of the function multiplied by x, right? You think of it. First derivative of f does what? The slope. Slope at 0 multiplied by x. Double derivative of f at 0, x squared, quadratic term, divided by 1 divided by 2 factorial, plus and so on. This is not something that is specific for signals. This is for all functions. Any function can be represented as value of f at 0 plus first derivative times x, second derivative x squared, and so on. That's your Taylor series. So we are going to use that Taylor series in our Butterworth filter design. So we'll just have that as a reference. Next, let's talk about filter specs. Ideal filter essentially has cutoff frequency, right? That's the spec. Because if you are within the bandwidth, then it is response is 1. Outside the bandwidth, it is 0. But for a filter that is a low pass filter, which is practical, you will have certain pass band, you will have some stop band, and you will have a transition band where you go from green to red, right? So I'm passing here, I'm stopping there, and I'm transitioning here. Inside the pass band, it is not going to be flat. In fact, it is going to have some ripple. That ripple, also called as pass band ripple, is delta sub 1. So essentially what you have is, you would expect this to be 1 constant. However, it goes 1 plus or minus delta 1. Delta 1 is essentially your pass band ripple. You don't want that to be very high, right? You want that pass band ripple to be as small as possible, so that treatment of the frequencies that are getting passed is fair. All the frequencies are fair. Now, at some omega p, what is omega p? Your pass band frequency, right? The pass band is from negative omega p to omega p. So I'm just showing the positive frequencies over here. You obviously have sort of the negative frequencies that are not shown here, but you know this there. So what is the pass band from negative omega p to omega p? Between the pass band frequency and the stop band frequency, you have a transition band. So the transition band is from omega p to omega s. On the positive side, on the negative side, it will be between negative omega p and negative omega s. At omega s, that's your stop band start. Frequencies above that are getting stopped. There is a ripple, however, in the stop band, which is delta 2, right? So if this is 0, then delta 2 is indicating the stop band ripple. You also want your stop band ripple to be close to 0, right? You want that to be small as well. Small ripple here, small ripple there, sharp transition. That would take you to the ideal brick wall filter. Let's see. Now, what we'll do is we'll start off with a third order Butterworth filter. Then we'll derive it. We'll derive the transfer function of a third order Butterworth filter, low pass filter. In looking at the form, observing the pattern in that particular transfer function, we'll project it for any order, n cap n order Butterworth filter. So let's try to take a look at the comparison between ideal brick wall and a practical Butterworth filter. The ideal brick wall is going to look like this, the black one, right? Between negative omega c and omega c is your passband, outside that 0. But the green one is your practical Butterworth filter. Close to 0, it is maximally flat, and as frequency increases, it smoothly goes down to 0. Right? Maximally flat close to 0, and as you are going away in the frequency, it goes to 0, smoothly goes to 0 as frequency increases. So this is your physically realizable rational transfer function. That's what we are after. We are trying to go for what that transfer function is going to be. And we are looking at a third order one. So let's start with the transfer function here, B of S. B of S is the transfer function of the third order Butterworth low pass filter that we are trying to design. Come up with an arbitrary third order rational transfer function. What do you have? A0, some constant, A1S. You have got a polynomial in S in the numerator. And you have also got a third order polynomial in the denominator because you are going for a third order filter. You have got some B0, some B1S, some B2S squared, some B3S cubed. Now, if you can find out A0, A1, B0, B1, B2, B3 such that you meet a Butterworth criteria, which is maximally flat and then smoothly goes to 0, then you have designed the filter, right? Your goal here is to essentially find these things out. Based on certain criteria, you want to find these out. Because once you find these out, you can factor the denominator, you know where the poles are going to be, right? Let's try to take a look at that. So earlier, we applied Taylor series for any function f, right? When we applied Taylor series for any function f of x, what did we find? It was f of 0 plus first derivative of f at 0 plus second derivative of x at 0 divided by 2 factorial and so on. That's exactly what we are doing over here. P of j omega, which is your frequency response of your Butterworth filter, the magnitude of that is being considered as the function of x. So that function of x, the first term was what? Evaluate the function at 0. Okay, so the magnitude of b of j omega at omega equals 0. Next, the first derivative of the function evaluated at 0 times x, or in this case, omega. Next, second derivative of the function at 0 multiplied by omega squared. You also have the 1 over 2 factorial. This is simply applying the Taylor series approximation not to an arbitrary function like f of x, but to the physically realizable transfer function in b of j omega. B of j omega representing the frequency response of your third order Butterworth filter in this case. Now, what is the strategy? The strategy is you want to force this frequency response to approximate the h of omega. What is h of omega? That's your ideal filter. You want to make this guy as close to this as possible. So we are going to pick the undetermined coefficients that are highlighted in green such that this guy matches this guy as much as possible, right? So what we are going to do is as many derivatives of b of j omega are equal to 0 as possible. We are going to set as many derivatives equal to 0 as possible, which essentially makes it maximally flat. So when you are, so see, we are not doing the evaluation at any other omega. We are doing that evaluation at 0 here, right? All these omegas are evaluated at 0. What I mean to say is, you could have done the Taylor series expansion at any time, right? That don't have to do it just at 0, but we are doing it at 0 because we want that to be maximally flat at 0. So we will try to find the derivatives. We'll try to set them to 0. What is, instead of considering b of j omega, we will consider b of j omega squared, because when you do that, the math becomes simpler because the complex terms gets cancelled out. And then later on, we will throw away. We don't even need to throw away because this is going to give us the transfer function, b of s multiplied by b of minus s. You can throw away some of the poles that you get later on. So magnitude of b of j omega squared can be written as b of j omega multiplied by b conjugate of j omega. This is complex conjugate, which is also the same thing as writing b of s multiplied by b of minus s with s equals j omega, right? Only the frequency response from the transfer function b of s. So considering that, what do you have? B of j omega is this. What did we do here? We simply took our b of s and put s equals j omega in there, and we found this. And for the right, what do you have? B complex conjugate of j omega. Everything the same, except instead of s, now you have minus j omega. If you have a function here and you have a function here and you're multiplying them, multiply it out. But don't write the results in a complicated manner with a's and b's. Instead, write it in c's and d's. For the numerator, you will have an omega squared term. You will not have an omega term because that would have cancelled out. Now you see why we considered complex conjugate. In the numerator will have some constant term d0 and some term omega squared. Similarly, in the denominator, you will have a constant term, a squared term, a power of 4, and a power of 6. All the other ones would have cancelled out, right, because of them being complex conjugates. Now, in our earlier goals was find A0, A1, B0, B1, B2, B3. Now our goal is slightly different. Find D0, D2, C0, C2, C4, C6, right? Instead of finding A's and B's, and now we are finding C's and D's. And the convenience is what? Because we considered complex conjugate, you didn't get any J terms. You didn't get any complex terms, which is why the derivatives are going to be easier with respect to omega. So now let's put it in the Taylor series. We are expanding the function magnitude of b of omega squared, right? We are expanding this using Taylor series for omega equals 0, right? At omega equals 0. So what do you have? Function at 0. First derivative of the function at 0 with omega squared, right? With omega squared. The omega squared is now going to be your x, because this is going to be x, this is going to be x squared, this is going to be x cubed now. Next, 2 factorial division, second derivative at omega 0, omega to the 4, plus and so on. We want to set all those derivatives going to 0, right? So what do you have? All of this at 0, what is that going to be? 0, 0, 0, 0, d0 divided by c0, right? Okay, just put in there. So this is giving me this. And we want that to be a 1. All the other derivatives we want to go to 0, right? And so that sort of, take a look at this. The green guy, the constant term should give you a 1, and all the derivatives that you have, because you want that to be maximally flat, all the derivatives should go to 0. We got that constant term to be d0 divided by c0, and you want that to be a 1 there. How about the derivatives? You took that function, you differentiated it twice, you plugged in omega equals 0, and for all of this, you get this. Omega squared carries over. You want that to cancel out. You want that to go to 0. So you want what? D2 to equal C2 D0 divided by C0, right? You want that to be equal to this. We know C0 cannot be, so this cannot give you 0 because that has a constraint. C0 equals D0. Next, Similarly, you differentiate twice, evaluate at 0. You want all of that to go to 0 as well, and so on, right? As many derivatives as possible, they will have to go to 0. What you got from here is, if you want this guy to go to a 1, then you got d0 equals c0. And if you want this guy to go to 0, then you got d2 equals c2. And because you want this guy to go to 0, you will get c4 equals 0. Plug all these guys in here. What do you get? So far, you get the magnitude of b of j omega squared, right? We are considering the square of the magnitude, will be 1 minus some coefficient c6 omega to the 6 divided by c0 needs to be found, c2 needs to be found, c6 needs to be found. So we went from finding A's and B's to finding C's and D's, and now we are, okay, I just need to find 4 things, actually 3 things, C0, C2, C6. So I need to use my second criteria. The second criteria is, as the frequency goes to infinity, the frequency response of this Butterworth filter goes to 0. Smoothly, right? Smoothly goes to 0. Now, for this, what we will do is, instead of using omega tends to infinity, so we want omega tends to infinity. So what we'll do is consider 1 over omega, which is your v, and we'll make v go to 0. You guys see what we are just finding the reciprocal and trying to make that go to 0. So we are going to expand the same magnitude of b of j omega squared, but now with respect to v, which is 1 over omega. Earlier we were doing just for omega, but we'll do it for v equals 0. Earlier we were doing omega equals 0. So instead of omega, we have 1 over v over here, 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 and here. Simplify, you get this. Our goal still is to find C0, C2, C6. We will expand this using the Taylor series, which means what? Function evaluated at 0 plus derivative of the function at 0, omega. Sorry, in this case it will be v. Next, second derivative at 0 multiplied by v to the 4 and so on. So when you evaluate the first term, you get a 0, because we are actually right. So if you take this, plug in v equals 0 here, everything is 0. Right? You get that 0. First derivative, evaluate at v equals 0, multiply by v squared. Next, second derivative at v equals 0, multiply by v4, and so on. Simplify, what do you get? This goes to 0. First derivative evaluated, it goes to 0. The second derivative goes to this. The third derivative goes to that. All the math over there is not shown. So, that it satisfies. Next, this is 0, this is 0. We want all of these to go to 0 as well, right? So if this has to be 0, we want C2 to be 0. So now the C2 is 0, plug in over here. What do you get? C0 was 0. Right, C0 we don't know yet. C2 we know 0, right? So this term has disappeared, this term has disappeared, this term has disappeared. So what we are left with is C0 divided by C0 plus C6 omega raised to 6. So by looking at this smoothly going to 0 strategy, our magnitude of the frequency response of this filter has come down to evaluating 2 coefficients, C0 and C6. I can divide everything out by C0. I get 1 divided by C6 divided by C0, omega to the 6. And if I define this to be 1 divided by omega c, where omega c is your cutoff frequency, so I'm defining this, right? I'm defining C6 divided by C0 as 1 divided by omega c power 6. What I'm left with is 1 divided by 1 plus omega divided by omega c, everything raised to 6. So that is function of omega, where omega c would define your cutoff frequency. This is in 6. How many poles does this have? 6. 3 of them will be in the right half, 3 of them will be in the left half. 3 of them will correspond to B of j omega, 3 of them will correspond to B conjugate of omega. But our goal did not have, we wanted our math to be simple, so that's why we considered complex conjugate. So essentially, we are going to throw away those other three. Let's see. So when you look at the poles of the transfer function, let's just try to wrap it up today so that we don't have to start all over again in the next class. Let's try to write this in terms of B of s, the transfer function. So what we have here is, instead of omega earlier, we are writing s, right? S instead of j omega. So before this, we had 1 divided by 1 plus omega divided by omega c whole cubed. Here we have a whole to the 6, right, raised to 6. Now we have s divided by j omega c cutoff frequency of the Butterworth low pass filter, with s as j omega, which gives us back our original function that we had decided. The coefficients are defined by C0 and C6. We are both combining that in omega c, which implies that when you take, so you took B of j omega and multiplied by B conjugate of j omega. In Laplace domain, what is that? B of s multiplied by B of minus s. So B of s multiplied by B of minus s is going to give you this transfer function. What are the poles of the multiplication of B of s and B of minus s? Those are going to be essentially the roots of the denominator. So how can you find the roots of the denominator? Well, s divided by j omega c raised to 6 has to equal -1, right? S has to equal -1. But -1 can be written as this in general, e to the j pi 2k plus 1. What is that? Odd multiples of pi. Odd multiples of pi will always give you -1. You guys agree with that? See, from 0, real axis, 1 pi, you get to -1. 1 pi, 2 pi, 3 pi, you get to -1 again, right? Every odd multiple of pi, you will get to -1. So what you have here is s divided by j omega c raised to 6 is this complex exponential with k equals 0, 1, 2, 3, and so on up to 5. Why? Because I only have 6 values there. So how can I write s? Well, you can just bring this out over here, take the 6th root on both sides, you get j omega c e to the j pi divided by 6, 2k plus 1. So instead of being odd multiples of pi, because you took the 6th root on both sides, this became odd multiples of pi over 6. J omega c with this complex exponential, omega c being the cutoff frequency. Next, j can be written as e to the j pi over 2. Omega c is written as is, and e to the j pi over 6 odd multiple written as is. Let's try to evaluate that for different values of k. Only 6 of them to consider, 0 to 5. If you plot it out, what do you get? You get pi over 2 plus odd multiples of pi over 6. Try to find the angle. K equals 0, you get that. K equals 1, you get pi. K equals 2, you get that, and so on. What are you getting? Everything is at a distance of how much? Omega c. And everything is separated by an angle. What is that? 90 plus odd multiples of pi over 6, right? So what do you get? When k equals 0, something that is omega c away, but at that particular angle, right there. K equal 1, get that. K equal 2, everything is omega c away, right? Radius of this is omega c, cutoff frequency. But you got 6 ones, 6 poles. 3 of them stable, 3 of them unstable, shaded in red. So I'm not going to need the 3 on the right-hand side. Why? Because I considered B of j omega with B complex conjugate of j omega. I'm going to throw away the ones that are on the right-hand side. But they are always, the poles are all going to be omega c away from the origin, and they're also going to be pi over 3 degrees apart from each other, right? Odd multiples of pi over 6. So filter must be stable. So you pick the left half plane poles that represent B of s. So you get 3 of them, right here, here, and here, when k is 1, 0, 1, and 2. All of them are going to be omega c away from the origin, and all of them are going to have these angles, pi over 2 plus 30 degrees, pi, and pi over 2 plus 5 pi over 6. So that is this point here, and this point here. And then using tricks, then you can find out what is this value, what is that value. I'm sure you guys can do that. So to essentially fill out the pole zero plot. So what is the pole zero plot? It has 3 poles, 1, 2, and 3, corresponding to k is 0, 1, and 2. Now, once you have the poles, you can rewrite your B of j omega, right? What is B of S? So from here, all of this, right? B of S is some function in S, all of, and then the denominator, which is a polynomial in S cube. I know what that is going to be because I know the factors now. Omega c cubed. Why is omega c cubed? Because when it is at 0, we want it to cancel out. We want it to give that a 1. So if you multiply this with this with this, you get a omega c cubed. We want that to cancel out, which is why we make the numerator omega c cubed. And in the denominator, you see all the 3 poles of the Butterworth filter that we had derived. Everything omega c away at angles that are spread out by 60 degrees. That gives you your final transfer function of the Butterworth filter. A cubic omega c, just a constant, given a cutoff frequency that is found. But in the denominator, what you have is a cubic in S, a polynomial in S of the 3rd order, giving you a 3rd order Butterworth filter. It has 2 functions, one maximally flat close to 0 and smoothly goes to 0 as frequency increases. We have leveraged Taylor series to do that simplification. Now, what is going to happen as you increase the number of, so as you go from 3rd order Butterworth filter to say 5th order, 6th order, nth order, what is going to happen? For 3rd order, you got 3 poles, right? For 6th order, you're going to get 6 poles. So the number of poles that you have are keep going to increase, which also means that the separation between the poles is also going to change, right? Over here, you can see that the separation is consistent, right? The separation between the poles is always, say, odd multiples of pi over 6, right? Pi over 3. As you are increasing the number of poles, the separation, the angle between them is going to keep reducing as you increase the number of poles. But they're always going to be omega c away from the origin, the cutoff frequency. So that will be a topic for our discussion when we come back. All right. I know that we talked a lot of math. Review it, please. All right, let me stop recording here. No, what is that? Not in there. But see, not the derivation, but what I'm hoping is for any given n order filter, you should be able to say, oh yeah, I'm going to have poles here, here, here. It's going to be the angle is so much different. That right away that you should be able to say the answer. That's all. What is that? How many lectures left? So I think I have three lectures. You too, Evan. So we have Monday, Thursday of next week, and then we have Monday of the following week. Right. So we have 3 lectures. What is that? Everything about poles zeros. What is happening? What is a lot of maths?
Count for this one. I saw you got this 11. That was from minus y prime. So that's minus 1. And plus 5 times negative 2. So minus 1 minus 10 is minus 11. There should be another constant, I thought, for this one.
No, it's not, right? That's what he clarified. It should be 0 for that. Yeah.
Oh, right. Right.
No problem. All right. Yeah.
I think there were way to do that. Are we just do the Laplace and use the
Fourier.
regional somewhere?
Oh, no. Don't do Laplace.
Yeah, because it says band limits. It's
Right. Just in frequency, it should be limited.
oh, so it's basically just
Omega.
we do the like
Fourier transform.
Fourier transform, and as long as staffing is not like as long as staffing is converged, it's band limits.
It's limited. Like it should go to
Limited,
0.
Okay.
If it is not going to 0, if it's like this, then it's not band limited. Hey Dan, what's up? B of S is the transfer function of the filter. We never used impulse response for the discussion today. We just used the transfer function.
But if we convert it to the time domain.
Yes, we get the impulse response of the third order Butterworth filter.
And this filter is special because you said the frequency is always
It's a practical way to get as close to the ideal brick wall filter as possible.
brick wall.
Brick wall, ideal, yeah. Rectangle. I know, a lot of math today.
Yeah, you did the Taylor series.
Yeah. Well, Taylor series is just a way to express a function using its derivatives. But we use that for our proof. But I'm sure you guys see Taylor series in your math classes, right?
Yeah.
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 There you go. Yeah.
I'm gonna have to rewatch.
I think in this same lecture last year, I may have gone a little bit slower.
Well,
So-
this was also like by this time I dropped.
Oh, okay. Oh, not everybody teaches this. So, yeah, I don't think Professor Yazici would have done this. Yeah. I don't think you were below 20.
No, I was like a 37.
So, like you,
I was shooting for at least a 50.
I know. 55 was an average. Yeah,
It's not terrible.
you are on a yes. Yeah. Okay. Do you? When can you meet? Tomorrow, what time can you meet on WebEx Teams?
Schedule something for tomorrow.
Like 12:30 until 12:30, I'm in class. But 12:30 after 12:30, I can meet.
Okay, yeah, that's what.
Okay. So how about 1? Okay. Just reach out on WebEx Teams. And then, yeah.
Did you know that?
All right. No problem. Okay. Guys, I need to record a video of me recording a video.
You record a video? I thought you record a video.
Yeah, so I have to show to the other faculty members how I do in-person class.
Oh.
So I have that. I'm going to set it up over there. I'm going to record. I'm going to record how I record. Yeah.
I want to get into more embedded systems.
Ah. Yeah.
And well, first question is, I have a project idea where I built like a radio, using some of the stuff we learned in signals with frequency, like modulation,
Nice. Yeah.
and like embedded systems. Is that a realistic project?
For what? for like yourself or yeah, absolutely, yeah.
All right. Second, where do I learn more information about going on?
I don't know if there's a class in ECSE that teaches real-time operating system.
Yeah, I figured I'd have to learn it a little bit myself, but
Yeah.
I already had
I
this.
I don't because I've not learned real-time OS. I think I did some programming there, but that was 25 years ago. Embedded OS. Are you in good terms with Wilt?
I guess Schwartz over the so I didn't really talk to him very much. But
Okay.
I mean,
I'm not sure. I'm not sure if he does anything in this area.
Alright.
But because he teaches microprocessor systems and he does light tech, maybe there is an overlap with RTOS. But other than him, I don't see anyone.
okay, so it's just
Yeah.
all right.
I think if you want to learn and do some projects for yourself, best way to do that is go on YouTube. Just yeah. I think you will be spending less time if you do that.
Okay, that makes sense.
Yeah.
Absolutely.
And you
Somebody
did. Yeah.
finds it.
Yeah. You just try to learn using videos, some articles here and there, and then whatever problem you have, you Google. Like just as everything we Google. Well, how do you do this? And then you get the answer. That's the only way to do it. Yeah. Even if you took a class on this, I don't think it'll be very slow, and you will sort of like, oh, I need this to do this.
Yeah.
You may or may not reach there.
Okay.
Yeah. What's up? Yeah.
Closely that this one, this omega c is.
Okay, FC.
Oh, this is FC.
Yeah.
Okay. No, never mind.
Yeah.
Yes, and for the solution for the SAM 2,
Yeah.
I think for twice derivative, we need some of the impulse functions, but actually this solution does not show.
Which one over here?
Part and the lead parts. Maybe we need some impulse functions.
No, we don't. Why will you need pulse?
If we only take these parts, this is the second order and this is the first order, and over here we take a derivative, we got this one and this one, correct? And this is this one, and over here is this one.
Yeah.
And for this one, if we take the derivative of it, I think it should be like this one, this one.
Right.
So,
Yeah.
So I think maybe for here we
need to add the. Yeah, you're right. Yeah. Did you have that on your solution?
but I did some of the calculations incorrect.
Oh, okay.
We so for the if for the other questions, I would like a grid request. I just send you
Email. Yeah.
and you check
Before Monday.
before Monday. Okay, thank you. I'll just send it to you. It's okay.
Yeah.
It's a question.
Yeah.
But so about the kind of computer that I talked about, I already purchased some parts and I already assembled the core part. Actually, the core stuff works, and now it's just the rest of thing that I want to use patch and extension cable to the panel. And also, I have to print a bracket to hold everything. Yeah. So now my question is, I have purchased a lot of those extension cable from Amazon, which is the only way I can,
Buy.
find them. Yeah,
Yeah,
they're highly customized.
yeah,
Some of the part,
Yeah.
and that cost me a lot.
Yeah.
I mean, all the I/O system that cost me more than half of the budget. Then the core system. Yeah. So I'm just wondering if there's any better way, to find supplier and to purchase these kind of thing. I know DigiKey, but they send standard parts.
Yeah.
Like resistors, inductors, yes. But if you just want a USB cable with one of the angle at, the type A
90, yeah,
and
okay.
another angle at type C, that doesn't work. And typically,
So your standard list of distributors is going to be my answer. Did you check with Mouser? Mouser, Mouser. Mouser is like DigiKey, but
yeah, another supplier.
yeah, another supplier.
Yeah.
But beyond that, you would need to look for suppliers
And they are
that
still
just do
expensive,
that.
actually.
What is that?
They are also expensive.
Oh yeah. They will be expensive. I don't think there's a way for you to work around that.
So another thing really interesting that I was searching kind of similar parts, and I just want to evaluate how much it would cost if I'm gonna assemble this in China.
Oh, if you have that option, do it there. Don't do it
Definitely,
there.
I want, but if it's COVID, I can bear, I probably just can't go home and shipping from there.
You at least do 5 times less expensive. At least 5 times.
Yeah, the case is that if I just want to buy, say, a 4-pin connector, I have to buy the entire thing.
Yes.
here.
Yes.
And on Amazon, it started at $5, and typically that's going to cost you like 10, 20-ish. So basically, in order to just make one customized part, that's going to cost me like over $50.
There's no other solution.
Yeah.
There's no other way to get around. The only way is if you go to tech dumps everywhere and find out parts.
And I find the parts,
Uh,
on AliExpress or something.
Yeah,
That's already made.
Yeah.
They have to ship.
It's a very expensive thing when you do this customized in small quantities. You are right.
But apart from that, it actually works like using Y3B. It does the basic decoding. I mean, almost all the decoding programs that can run in the background, and I can host a web service.
Oh, okay.
Web server that does. It's like forwarding whatever they hear on the spectrum to the Ethernet, and from some of the clients, they just open a browser and visit the page, and they can try to tune to different.
Nice.
You can see the spectrum actually.
Yeah.
Spectrogram. That's how I'm saying.
Yeah, spectrum. Nice, interesting. All right, guys, I'm going to record. Yeah. I'm all ears. I'm all ears for that. All right, I'm going to, well, should I end? How can I, come on, man.
I know. But probably just.
Sometimes this happens. If I just close my lid in the laptop.
No, he'd always do this.
Yeah.
And he's not even in the class, man.
Oh,
Yeah, he's not in the class. I looked at his SIS. He's not even in the class. No.
Write a script for this kind of thing.
Yeah, but he enrolled and then he dropped, I think, at some point because he's not enrolled in the class anymore. He's still coming to class. I don't know.
Like join this class based on what time? Yeah. No, this happens sometimes. I mean, last semester I was taking algorithm, and I know half the class is doing that.
Oh my gosh.
Because that instructor is terrible.
All right, see ya.
Every time we end up.
Yeah. All right, I'm ending